Good afternoon and welcome to day 3 of reInvent 2016. We are delighted to be here to talk about building real-time streaming analytics using AWS services. My name is Radhika Ravirala. I'm a solutions architect based in Atlanta. And joining me today on stage is Nabil Zaman, software engineer from Quantcast. I'd like to begin this session with a quick poll. How many of you are currently using Kinesis in your environments today? Wow, it's almost half the room. It's exciting, guys. I'm sure you'll find this session informative. So I'd like to start the session by giving you a quick primer on the Amazon Kinesis platform, and then really expose you to some real-time architectures built by some customers using AWS services. And then Nabil will walk through a journey that they have gone through building real-time streaming campaign analytics using AWS services from the lens of a practitioner. So with that, let's get started. Amazon Kinesis started off as a single service launched back in 2013 and has evolved into a platform now comprising of 3 different services. We have Amazon Kinesis Streams, which is a service that lets you continuously capture terabytes of data per hour from hundreds of sources and process the data in real time and also specify a destination if that's what you choose to do. For developers who really appreciate or like the convenience of their data being sent to a specific destination, we have built Kinesis Firehose. And the newest member of the Kinesis family is Amazon Analytics that lets you run SQL queries, ANSI standard SQL queries on streaming data. So let's take a look at some of the highlights of each of these services. Kinesis Streams is actually designed with the goal of making it really simple and easy for developers to start writing streaming applications. It's a service that lets you create a stream and simply set a capacity that you wish in terms of shards. And once you set your capacity, you can scale up or scale down the capacity by simply increasing or decreasing the number of shards that you have defined. It's a system that's designed to allow you to write real-time applications, whether you're using Apache Spark or Storm or going the serverless way with AWS Lambda. It's also engineered with cost in mind, meaning that like many AWS services, AWS Kinesis is a cost-efficient solution for workloads of any scale. A lot of developers have told us that they like the convenience of micro-batching their data and that data being delivered to a destination of their choice, namely either S3, Redshift, or Amazon Elasticsearch. For those developers, we have built a service called Kinesis Firehose Delivery Stream, which allows you to capture and deliver data to these destinations without having to write any code or manage any infrastructure. In addition to capturing the data, you can optionally compress as well as encrypt your data before it makes it to the destination. In addition, it allows seamless elasticity. You don't have to worry about increasing or decreasing your shards. We take care of that seamlessly underneath the hood for you. So there's a lot of automation built in, a lot of administration that is taken care of us behind the curtains. And the newest member of the family is Kinesis Analytics. In simple terms, Kinesis Analytics is a service that lets you run SQL, ANSI standard SQL on your streaming data. It's a real-time streaming SQL engine that can run your queries in sub-second processing time. Like the other services, it's built with a lot of good design goals. For example, once you start streaming your data, Kinesis Analytics can automatically infer the schema, and it will let you either edit that schema or impose a schema of your choice, and you can start running your SQL queries. In addition to running ANSI standard SQL, we have also extended that functionality to include many Windows functions. And the reason for that is Stream, as you all know, is unbounded. And having a window function will allow users to compute your queries within a certain window. Like Kinesis Firehose, it elastically scales to match your data throughput. A lot of times, your data throughput, your data rate flow changes. Your complexity of the query also changes. We increase the capacity, the CPU needed to run, process your query underneath the hood without you having to intervene for anything. So let's take a look at some of the architectures, real-time architectures our customers have built using these technologies. So a colleague of mine once said, a journey to building a good real-time pipeline starts with a simple one. So here is a simple architecture built by one of our customers, Hearst Corporation. Hearst Corporation have multiple digital properties. If you're familiar with Cosmopolitan and other magazines, they are behind those magazines. They analyze a lot of data to make recommendations or deliver useful stories to their customers. So their architecture consists of streaming data from their browsers as well as from their mobile apps into a Kinesis stream. That data is processed by an EMR cluster with Spark running on EMR, and the processed results are sent to S3 for downstream consumption. They also have a need to capture this real-time data as it is coming and archive it to meet their requirements, other regulatory requirements. To satisfy that requirement, the streaming data that is pushed to Kinesis streams is also consumed into a Kinesis delivery stream shown below via AWS Lambda function and sent to S3 for long-term storage. So here is another design built in a truly serverless fashion by Just Giving, who are the world's largest social platforms for giving. This is a time series analysis on a stream of web events. What you see here is a number of producers putting or writing data into a Kinesis streams. That data is picked up by a Lambda function to perform in-memory calculations on the real-time data for time series, and that running counts is sent to a DynamoDB into a summary table in the DynamoDB table. As soon as the data lands in DynamoDB, another Lambda function picks up that data and processes the data and sends it to CloudWatch for dashboarding. So this is a little more involved architecture, but yet it's very simple because it uses Lambda and DynamoDB, which are truly serverless services. For many systems, location where the event occurred is highly important. For example, think about a scenario where an alarm goes off in one of the warehouses, maybe around the world. That event is of no use if you cannot pinpoint exactly where that event occurred. To accommodate such scenarios, we have built a solution engineer from Amazon built a solution architecture that will combine real-time streaming data and references the geographic data residing in a Redis cluster and makes it available to a web server, Node.js web server running on Elastic Beanstalk. Combining those two data allows customers to really create good visualizations like the one you see on the right. It's a heat map showing where the events occurred over a period of time. And there are many times customers want to include both batch analysis and real-time analysis in their systems. An example of that nature is built by Smart News. Smart News is a news discovery app that delivers best stories to their 18 million plus users around the world. They have multiple teams processing real-time data for various purposes. Now, to meet the goals of these teams, they have built a sustainable data platform that can serve all these teams with the data they require. In this example, they have built a Lambda architecture that serves their news division as well as their product division. Their architecture comprises of, by the way, is everybody familiar with Lambda architecture? So Lambda architecture is a data processing architecture that allows you to combine both batch analysis and real-time analysis in a single system. Their architecture comprises of collecting user activity data that you see on the left-hand side, generated by their mobile applications, and also collecting data residing in their tables, the RDS instances residing in many of their databases. The log data, the user activity data, is sent to FluentD, which is exported to S3 as well as Kinesis. The data residing in their tables is exported via an OSS bulk loader into S3. Now, as you can see in their batch layer, they are taking the data and processing ETL, performing ETL tasks to convert their text files into columnar format and making it available in S3. They also have a serving layer that creates views and indexes them and makes it available for querying via Presto. Coming to the speed layer, the data sent to Kinesis streams is consumed to look at the trends, the articles that the customers are looking at, and deliver the most relevant or the most appropriate article to the end user. So because we are talking about ad campaigns, let's look at another real-time architecture that comprises of looking at anomaly detection using Kinesis analytics. So in the digital advertising world, analyzing real-time clickstream data immediately is of immense value. One way digital advertisers or marketers make sense or monitor their ad effectiveness is by monitoring their click rate. So for those of you who are familiar with click rate, great. But for those of you who don't know, when an ad appears on a website, it's called an impression. And when an user clicks on the impression, then it's called a click. So the click rate is computed as a ratio of the clicks to impressions. Click rate can be computed using the Kinesis analytics service here, and we'll walk through the architecture right now. So one of the things that I want to touch upon before we go into the architecture is that what we are doing here is that a click rate demonstrates the ad performance. The higher the click rate, the better the ad is performing. But advertisers also want to look at the low-end click rates, which might indicate a bad image or maybe a bad bidding model. So here is the architecture. Users send their traffic in the form of HTTP GET requests with a query string and a header. That requests are consumed by Amazon API Gateway. API Gateway is a fully managed service that lets developers create, publish, monitor, and secure their APIs. Now, in this example, API Gateway is acting as a proxy service to Kinesis streams. It actually takes the HTTP request and converts the HTTP GET request and query string into a JSON message. That JSON message ends up in a Kinesis stream, which is consumed by the Kinesis Analytics application. Now, the Kinesis Analytics application is actually keeping track of the count of clicks and impressions in 10-second tumbling window intervals. Once it computes the clicks and impressions, it calculates the click rate by simply taking a ratio of that, and then it passes the click rate to what we call is a random cut forest function. This is an analytical function used in machine learning by many companies, and it lets you detect anomalies. And the way it detects anomalies is as the data is flowing, this function, random cut forest, computes a score for the incoming data. It identifies a pattern, and anything that doesn't fit the pattern has a lower score. So the clickstream data, the click rate, is passed to a random cut forest within Kinesis Analytics application, and that score is put back in, is picked up by a Lambda function. Now the Lambda function has the logic built in to detect the anomalous data in that results that are being sent, and it immediately sends a notification via SNS to the end user to take some kind of an action based on that. So this is the story of different types of real-time applications that you can build. I encourage you to build your own real-time streaming applications and share it with us. With that, I hand it over to Nabil to walk us through their journey to building.
Cool, thank you, Radhika. So hi, my name is Nabil Zaman. I'm a software engineer at Quantcast. And before I get started on the actual main topic, I wanted to introduce a little bit who we are at Quantcast and what we do to frame the rest of this talk. So Quantcast is a leader in digital advertising. We have partnerships with millions of publishers across the world, and we're able to leverage those partnerships to see really deep insights into the internet activity of users at a really frequent rate. I think the average US internet user, we get hits on about 50 times a month. And so tracking that activity lets us really improve the relevancy of the digital advertising that we're able to provide on behalf of our clients. So we consume about 100 million bid requests per day, and about 40 petabytes of data is processed in our compute cluster to meet our business needs. We have 180 engineers globally in 4 offices, and we're hiring. I'm contractually obligated to let you know that we are hiring. You can reach us at reinvent@quantcast.com. We'd love to hear from you if anything today sounds interesting, if you want to learn more, stuff like that. So Quantcast has a lot of on-site infrastructure to support our business needs, but we've been making a push this last year or so to move a lot of things into AWS, and there are a few reasons why. Firstly, Amazon S3 is a business continuity solution for Quantcast. We have business critical data that we rely on to continue serving ads and earning money. But if there is a disaster scenario, we need to be able to fall back on something to be able to continue while we recover. And S3 provides that avenue. We have 8 petabytes of data backed up there. Additionally, AWS, I think this is a reason why a lot of people try to use it. It lets us experiment with new products a lot better, and a lot faster, really. That faster is better. What I mean by that is normally, in order to build out the architecture, the infrastructure to support a new product, you have to make a huge devotion of resources. And really with AWS, you can move a lot more quickly, experiment with things that really you're not sure yet if will be worth it at the end, but you can move rapidly enough to make those experiments and make those pivoting decisions as you go along. We also provide our teams with total ownership, so you don't have to interface with another team that owns the hardware that your services are running on. Because you own it from end to end, any problems, any like new tweaks, they don't have to deal with that extra barrier. And in general, working in the cloud solves a lot of headaches, but comes with its unique set of challenges that I kind of want to emphasize as I go along. So before I take too long, let's move on to the journey that my team and I took over the past year building a real-time campaign analytics product in AWS. So what is the problem that we're trying to solve? We have, like I said, these servers that we own that are performing real-time bidding on ad exchanges around the world to serve ads on lots of different websites. We have about 2,000 servers performing these activities, and they're dealing across them all about 2 million bids per second. As these bids occur, we update various metrics internal to our bidding processes to get a look at how the bidding is proceeding, whether we're going too slowly or too quickly, or if some issues come up along the way. So a number of metrics get incremented or decremented or so on. And we want insight into these metrics at close to real time. So about 50,000 unique records, so for some numbers, are being aggregated in each of our bidding servers. With 2,000 servers, about 100 million records that we need to collect and provide some view on. So how do we get that data from our servers to downstream users and services? Of course, with AWS. So the first approach that we took, starting in our data centers, we decided that these metrics are being stored internally and monitored, and we're going to emit like a dump state every periodic interval. 10 seconds or so gives us roughly the real-time view that we want. So when a bid happens, at most 10 seconds later, it's reflected in a new message that the server emits to some centralized location. The record that exists for this set of metrics, for every active ad campaign, we have a record or some number of records based on some additional factors. But before we send it along, an important feature is we choose to bundle these records and compress them. So we're not sending 50,000 individual messages across the wire. We send a lot fewer larger messages because we see really good compression characteristics in our data. And this ends up being important as we go along. So from our data centers, entering into the AWS realm, we enter Amazon Kinesis. Radhika already did an excellent job explaining Kinesis. We're using Kinesis streaming specifically, but these are some of the reasons that we chose to go with it. Kinesis persists data, I think by default 24 hours, but you can expand that to up to 7 days for additional cost. But this means that in the event of any failure, you can recover by replaying that data. Multiple applications can read from a single stream. The consumption of data off the stream is non-destructive. So if there's some really important data that's being passed through a stream, you can have multiple applications that are interested in consuming it do so. You can scale the data rapidly by just increasing the number of shards. This, without any real interruption of service, this gives us a lot of flexibility to expand the product in the future. And pertinent to our particular design, since you have to shard each message before it can know where to end up in Kinesis, we're actually sharding by the server identity. So each of our 2,000 servers or whatever know what their own identity is and tags a message with it. The reason we're choosing to shard by this particular value is because if we were to shard by something like the campaign ID, which has a more logical meaning, we would have to actually split that up into a single message for each of those IDs because you can't give multiple shard keys to the same message. So we're able to send a lot fewer messages, get better compression by just tagging each message we send with the server identity and moving on. The data is then consumed by consumers running an EC2, and that data is then written to DynamoDB. We have a time series database that provides historical views on this data, and then we run a query service on top of this, and downstream users and services are able to access that data through an API endpoint that we expose, and the query service just goes back into Dynamo to provide the particular insights that the users are interested in. So to stop here, want to go into a little of how much this is costing us right now. We have to collect about 10 million records per second. It was 100 million divided by 10 because it's every 10 seconds. And the monthly cost for Kinesis and EC2 is fairly small. We don't have very demanding uses there. But DynamoDB ends up being really expensive here. To write at the rate that we need to, the provision write throughput is a lot of money. And we need to justify this, and we can't. So we need to try to make Dynamo cheaper. So in order to make Dynamo cheaper, we do some digging and find that our actual problem isn't quite as hard as we might initially think. Only a small subset of the metrics that we're collecting need to be accessed really rapidly. The rest of the metrics, we can expect a little more lag and latency, excuse me, and that is totally fine. So because we want to save costs on Dynamo, one of the simplest things we can do is reduce the rate at which we write the data. So every 60 seconds instead of every 10 seconds, we write data into Kinesis, it gets picked up at the consumer. It's the exact same process. We write a sixth as frequently into Dynamo and spend a sixth as much money. It's pretty simple math. But that won't cut it for some of our metrics. Some of our metrics, like how much money we're spending, how many impressions we've served, really vital things like that, need to be available more frequently. So at the same 10-second interval we initially intended, we have a second stream that is much smaller because we have fewer numbers really that need to track. And we're writing into Elasticache Redis. Redis, if you're not familiar, is another data store in AWS, or Elasticache Redis is at least. And it provides us with basically an in-memory data store. And it's really fast, but it's fairly feature-light. But because it's all in memory, we can't store too much. We have a rolling window of about the last hour of data that we care about in Redis, and this works fine because it doesn't charge you by your writes, which is great. So our architecture now looks like this, and this is how much we now have to spend. We're still collecting 10 million records per second or so now into Redis, and a sixth of that, larger records into DynamoDB, about 1.6 million. And the total monthly costs are significantly reduced. Dynamo is a sixth as expensive. We add another Kinesis stream, so it's a little bit more there, a little bit more EC2. We're also paying for Redis, but this is better, less than half as much. But we noticed something strange as we started scaling out, and I'm going to try to explain why. The way Kinesis works is when you send data into Kinesis, again, it's sharded, so every message ends up being sent into a single shard. And the guarantee here is that for any given shard key, that shard key will only appear in a single shard. So using the KPL and the KCL, the Kinesis libraries that are provided for reading and writing to Kinesis, and I strongly recommend you use these because they're great and they have a lot of features and they solve a lot of the problems that you'd have to solve yourselves. The KCL creates a single process for every consumer, for every shard that needs to be consumed from. So we have about 50 shards, so there are 50 consumer processes, like Java processes, that are running independently, not sharing any memory. And so what that means is we are having each of our consumers read basically all 50,000 unique keys and writing all 50,000 unique keys into DynamoDB in parallel. So instead of writing all of those keys exactly once, we write them all 50 times and have about 2.5 million writes per minute, not what we originally intended. This is simply because when we're sharding the data initially, each server has all of these records in it. It's sending them into a random shard based on its own identity. And so the data isn't organized by these keys. We can't expect the keys to only show up in a single shard. So this is a problem. The way we can get around it is by reorganizing our data. Just shuffling it is the thought we had. And we can actually employ more Kinesis to get this to happen. But before I move on, what I thought was about $4,200 per month for this product actually is well over $100,000. And you also can't even provision this much throughput in Dynamo without getting like super special permission. So it's not a good idea. So our architecture before looked like this, with 2 streams, 2 sets of consumers reading from those streams, writing to 2 disparate data stores, and a query service on top of them. And there was this conspicuous gap there this whole time. We can fill that conspicuous gap to make our lives a little better with another set of consumers and another Kinesis stream. And these quote-unquote shuffling consumers end up reading the data, which is originally organized by server identity, aggregating it and resending it into Kinesis by the actual key in Dynamo that we'll be writing to, a prefix of that key actually. But what that means is for any given key that we want to write to, only a single shard will contain that key. And so our consumers, that second set of consumers, are responsible for a disjoint subset of our key space. This means there isn't that nasty overlapping that amounts to wasted writes. We get to write exactly once for every single campaign we run, and again, writes in Dynamo are really expensive. So this is important, and we do it, and we test it out, and it actually costs what we thought it cost, and it's good. So these are the updated numbers, roughly. We have additional Kinesis costs, additional EC2 costs, but it's a lot better than spending $100,000 in Dynamo. So we're pretty good here. We kind of have a product that's working, but we want to kind of explore some other opportunities now that we're in AWS to make this a little better. So AWS Lambda is a really cool service. Radhika has already talked a little bit about it, but it has this whole concept of serverless architecture. You don't have to manage your own EC2 instances. You don't have to care about how they come up or when they come down or memory or CPU, none of this monitoring this stuff. It's just a huge boon to operations. It's a little more expensive for our use case. Just in general, if you have a fairly slow or bursty stream that isn't going to get data very often, AWS Lambda can be really good because it comes up, consumes the data, shuts down. You're not paying for when it's not active. But our stream is constantly running. We have lots of data flowing through the entire time. So it's a little more expensive. We spec'd it out. But this can be justified by the operational overhead. So we have this completely serverless architecture here. It's just replacing all the consumers with Lambda consumers instead. It's really easy to implement, but trying it out and scaling up the data, we noticed that it wasn't able to keep up with our Kinesis streams, and we don't know why. And we poked around the CloudWatch metrics, and that didn't really tell us too much. And our first impulse is SSH onto the box and profile it and figure out what's going on, and none of that's possible. I think there is an avenue of investigation through opening a support ticket with a Lambda team and pursuing that, but we already had a working solution, so we kind of just moved on. It's a little sad, but Lambda does not appear in our final design. Some additional optimizations that we made along the way, we have our consumers continually consuming data off of the Kinesis stream, but not actually writing every batch. They have an internal timer that they wait to aggregate. This just lets us have a configurable knob that we can turn where we can trade off data freshness for cost. We can write less frequently to DynamoDB, but at the cost of having the data appear later, or vice versa. And this is a really nice thing to be able to present to your customers. We can make this better if you are willing to pay the additional cost. This next point, and I wish I really had a diagram for this, but I don't because it's really hard to draw. So what we're doing is what is actually happening underneath the scenes with the KPL, the Kinesis producer library, is when you're sending a message, a Kinesis record to Kinesis to be consumed and stored, you assign a shard key, and the shard key gets hashed using some hash function that has good balancing, and that hash is actually what's used in a map to identify what shard it really ends up in. So you give it some key based on your data, it hashes it, and you're golden. The thing is, because this shuffling step involved sharding the second stream by the actual key in Dynamo that we eventually write to, there are a lot of those keys. Before, we're writing only a few messages, few large messages into Kinesis from each of our servers. But now our consumers are writing like 50,000 different messages, all fairly small. We don't get the same compression that we want. It's not as good. We can still manage it. We did initially. But what you can do instead is look up the shard hash to the explicit hash to shard mapping in Kinesis. The thing that underneath the surface the KPL is handling for you, you can query the API and get that mapping yourself. And any messages that would appear in the same shard, you can just bundle them together and give them the same shard key. It doesn't have to mean anything. You'll just guarantee they end up in the same shard, which is what you wanted in the first place, which is what we wanted in the first place. We want to make sure the same data doesn't appear in multiple shards. And we can guarantee that while having fewer messages by just bundling things together that normally wouldn't get bundled by looking up this map. It's cool and hard to explain. So the last optimization is simply we did some rate limiting on the consumer's writes to prevent Dynamo write failures. This is something you can configure as you provision your Dynamo usage. But yeah, so to do a final checkpoint, see where we are. These optimizations saved us a little bit of money. We're about $5,000 spent to build this product out, sticker price. So where did we end up? This is our final architecture. Things are in auto-scaling groups, writing into these two data stores that I've been talking about. The query services behind an Elastic Load Balancer, all fairly sane things to do. And it works pretty great. In terms of deploying all of this, we use a few different tools that I kind of want to plug. Terraform by HashiCorp is a really neat tool to be able to codify all of your architecture. You can represent everything in terms of scripts. This is very similar to CloudFormation, but there are some differences that we enjoyed from Terraform. So we've been running with that. But Terraform 1.0 and doesn't provide support for every one of AWS's services. So if it doesn't work for you, it might not. But I strongly recommend you look into it. Each of our services are completely containerized in Docker. This is huge. We can do complete replication of staging and tests and production environments by just having everything encoded in Docker images. Docker is awesome. And we initially set out to use Docker, and we ran with Docker, and we've never looked back. Jenkins, we have our own Jenkins build system set up to build and deploy all of this. It's nice. Multiple availability zones is really easy to configure throughout all of the kinds of things that we've done. Just you say you want it, and you say which ones you want. And there's some VPC configuring, but it's pretty simple. But multi-region is a little harder, and it becomes more expensive because you have to transfer the data across regions. So we're not really running with that. High availability is achieved through availability zones sufficiently because availability is in the name. Some possible future directions we've considered going with incorporating Apache Spark. Some of the consumer operations that we're doing can be done in memory, actually. The shuffling in particular is very reminiscent of MapReduce, and Spark streaming could do something very similar without introducing a second consumer step. But we've only played around with Spark so far and haven't really dived into the realities of that yet. Our scale will continue to grow. We have a bunch of plans for incorporating much larger data sets. We have about 50 shards in our largest stream and about 30 shards in the other one. The other data sets we plan on passing through Kinesis, another one's close to 300 shards, and then another one would be closer to 5,000 shards. Not entirely sure all of those will fly in terms of if that's the best way to solve those problems, but it's really exciting to try to push this. Once we have this kind of prototype working and getting value from this, we can really push the scale. And then there are a number of AWS features that have been coming out. Kinesis Analytics launched while we were building this all out, so we haven't really played with it too much. And then there's Kinesis Firehose that might actually make sense if Redis or DynamoDB end up as destination possibilities. And then there are some failure cases that you need to be able to handle in any sort of highly available system. If one of our servers goes down, we have auto-scaling groups. The Kinesis client library, the KCL, is really, really nice in that it'll reshard automatically for you. If it notices one of the consumers has dropped off, it'll reallocate the labor so everyone, all the data is still being handled. It's great. The server will eventually recover, and everything is kind of fine. Elasticache Redis, we worried for a while that a failure here, because everything is in memory, just means a complete loss of data. And we played around with it. We have replication so that it's not very likely, but if the entire replication group fails, you lose data. But we've configured our query service to be able to handle this kind of failure in that if Redis is unavailable, DynamoDB contains basically the same data, just less frequently. And so we can add some delay, but eventually when Redis does recover, we'll resume full service. And then we had some issues for a while with the presence of gaps and duplicates in our data. We have all of our data centers sending their data into AWS. We have several across the world, and the services that are doing that aren't super reliable, and we can't be sure that all of our messages are being counted. And so gaps are an issue we worried about. With Kinesis, there was an additional concern because Kinesis has the opposite problem where it's at least once delivery, so duplicates can occur, and you need to engineer around being able to handle that. If your data needs to be exactly once, you need to figure out how to do that well. We spent some engineering time to figure this out. We have all of our messages numbered, and we can identify when gaps and duplicates appear by caching some degree of some history of the messages that each consumer has seen. And then you can get rid of duplicates, and you can only monitor gaps. Once the message is gone, it's kind of gone. But we've found that it's well within the amount that's we can handle. So to summarize with some of the lessons that we've learned, in particular with respect to each of the AWS services that we've used, DynamoDB is very versatile and a reliable key value store. It has a lot of nice features. It's very highly available. And we haven't had that many issues with the cost of storage, but provisioning reads and writes will be an issue if you're not careful about it. If you are writing a lot into DynamoDB, it will cost you. So what we've found is it's maybe best for larger data sets with less provision throughput. Elasticache Redis has a fast feature-light data store. You scale the amount that you want to store in RAM, the number of IOPS you're performing in CPU, but large volumes of data isn't feasible, especially because if it goes down, then the large volumes of data are just all gone. But the small data sets that need to be written frequently and updated frequently, a moving time window in particular, makes a lot of sense. Right, Kinesis, you've already heard a lot about Kinesis, but in particular, checkpointing we found to be very useful. We've played around using multiple applications with with streams that a lot of our teams internally are interested in. They can just write their own applications to consume that stream, and none of them interfere with each other, and that's wonderful. Additionally, the libraries are great. We had some issues with the amount of CPU that was being used, but from what I've heard, more recent versions that we haven't upgraded to yet have solved that problem. Lambda is a really theoretically great way of transitioning computing. I would love to not manage my own servers, but investigating issues was difficult, and if you can't do that reliably, because issues will always occur, it has limited utility. And so just in general, AWS, I've already mentioned, rapid mobility and experimenting with products, having teams have complete ownership of their own infrastructure is great. Built-in tooling and monitoring, like having auto-scaling and elastic load balancing just provided for you is a really important feature that we take advantage of. But some of the costs to working at AWS, include you needing to really carefully manage your resource utilization. Basically, when you have, this is kind of a growing pains that we've had at Quantcast, where we have our own internal infrastructure and we're transitioning into AWS. But as we do so, we can't take advantage or take for granted the same things we did before. You've already bought your servers, you're not paying anything more for them, so you can kind of be haphazard with how you use them. That's not true in AWS, and if you're not careful about how much you're consuming, you will very quickly spend too much money. So engineering problems arise around cost optimization that didn't before, which was interesting to us. And there was a surprising amount of opacity, in particular with the limits set on your account, these like hidden speed limits that exist. Especially if there's something that you need to do rapidly, there's some scale you didn't anticipate, you need to quickly expand out some of your architecture to accommodate like Black Friday or something that you should have anticipated coming. There's a real risk of the scale not being available because of these account limits, I think meant to protect you, that can really bite you if you don't plan around them. So yeah, that's pretty much all that I have prepared. Thank you for your time. Really quick, again, I'm contractually obligated to let you know that you can apply through reinvent@quantcast.com. Please, we'd love to talk to you. Additionally, complete your evaluations. Please tell the world I'm great, and Radhika is great. And here's some related sessions for you to maybe explore if you liked what you saw today.
We're happy to answer any questions if you have any.
Yeah, for sure. We're going to be sticking around for at least 15 minutes.
Yes.